Hi and welcome to this installment of By Manufacturers Direct, Execs and Techs, where we sit down with industry experts and innovators to discuss trending topics concentrated in the surface preparation industry. In this ongoing series, we'll examine traditional methods and best practices, as well as review our industry's most popular pieces of equipment, while taking a peek behind the curtain of the engineers and manufacturers who build them. We'll also explore and experiment with commonly used products in addition to introducing new cutting-edge technology. Joining me each episode is our resident subject matter expert, former contractor, and current substrate technology president, Josh Jones. Each episode, Josh and I will discuss various aspects of our industry. We'll explore topics from both rudimentary and experienced perspectives in an effort to advance the knowledge of both beginners and seasoned veterans. Throughout this series, we'll ask our audience to help identify and nominate future discussion topics by subscribing to one of our online platforms and submitting your suggestions in the provided comment section. Hello, and thank you for joining us for our continued educational journey through surface preparation. My name is Kevin Hawthorne, and I'll be joined by our resident subject matter expert, industry patriarch, and substrate technology president, Josh Jones. Last episode, we launched our video series with a more generic or rudimentary insight into surface preparation. If you haven't had an opportunity to watch that episode, I would encourage you to do so. I hope you find today's discussion not only informative, but also beneficial to your business. With that, let's jump right in. Josh, as we discussed in our last episode, the primary function associated with surface preparation is ensuring bond performance, regardless if it's a coating, an adhesive, or really any material. Josh, in a recent training, you outlined 3 primary objectives associated specifically with concrete surface preparation. Can you outline those with a brief description of each?
Sure, I'd be happy to. Working from the top down, as the floor would be approached from a surface preparation standpoint, the first thing to do would be to clean the surface, or basically expose the base slab. So we're basically just trying to remove anything that's on top of that concrete to expose the structural concrete or the slab we intend to coat, completely open it so that we can inspect what we're going to be working with for the coating. The next step would be profile creation. That is what's specified by the manufacturer so the coating can stick, for lack of a better term. If a certain profile is required, then we got to make sure that that base slab has been profiled to meet that specification so the coating can absorb and also bond. Finally would be testing. That would be a pH test, a moisture test. There's a lot of different ways to do it, but we want to make sure that the floor itself, when it's completely cleaned and profiled, that it is in a chemical state that is acceptable to the coating. So there's no chemical interactions that could cause future problems.
With that said, do you have any recommendations for pre-application checklist or things that should be done prior to even getting started that would benefit you throughout the process and also the final result?
Yeah. The biggest problem that can be encountered is once the material is mixed, everything goes fast. And the reason being is because the coating, once it starts to catalyze, the clock is ticking for when it's going to start to react and the viscosity is going to rise. For that reason, before anything is mixed, the final things to check on the floor, a little bit to reiterate, is to make sure the profile is acceptable for the coating. That's been verified. That it's clean, that no other contamination has taken place since the last time it was prepared. And then also that we do have the results of the moisture vapor and pH testing complete, that the results are favorable. It sounds like a redundancy, but the reason we want to be redundant is because once that material is mixed, there is no time left to avoid a costly problem. There is no time to avoid an expensive mistake, really.
What are some of the common residual materials that could be included in that?
The residual materials
that could be left behind or that you need to clean to make sure that you're leaving a surface that's perfect for receiving a new application?
Oh, you mean any of the previous materials that were cleaned or need to be cleaned? Could be adhesive, it could be old coatings, it could be old sealers. Basically anything that's on top of the concrete that's going to inhibit the bond or really inhibit the absorption of the new coating to actually absorb into that floor and anchor into the pores so that it literally fuses itself to the surface of the concrete. So again, adhesives, coatings, paints, sealers, anything that's going to act as something that stops the penetration or absorption of the material is going to be something that could cause delamination later.
In your experience, what are some of the best cleaning methods to achieve that?
Depending what material is on the surface, it's certainly going to decide which is the appropriate cleaning method. But to list a few: carbide scraping, which would be bulk adhesive removal; diamond grinding, which is going to be for floor paints, thin coatings, adhesives; PCD grinding, which would be for the thicker coatings, thin set, old epoxies, old urethane cements; scarifying, which would be for the thicker mortar systems or thin set; and then finally shot blasting, which is really more for thin acrylic or cure and seal type materials, or any surface latents maybe on new concrete. But those are the 5 basic ways to clean the floor of whatever different kinds of contamination may be present.
Can you go into a little bit more detail of those, starting with the carbide scraping?
Carbide scraping is something that's been around actually for a long time on swing machines, which is essentially a square blade that's literally turned across the floor under a rotary style machine that slices or pushes the bulk adhesive from the concrete. It's not really known to be used for paints or any kind of resilient coatings like epoxies or urethanes, but for the flexible materials like adhesive, it works terrific to push that bulk material from the top of the concrete. It doesn't grind the concrete. It doesn't flatten the concrete. All it does is push that gross material that's sitting on top that can be pushed free before a subsequent process can be done.
Okay. You also mentioned diamond grinding. I know there's a lot of interpretations and a lot of perspectives on diamond grinding. It seems to be somewhat of a generic term. Can you go a little bit more in detail about what that entails?
Well, diamond grinding is the process that's going to turn the floor essentially white. As it removes that contamination, whatever it is on the floor, whether it's epoxy, paint, adhesive residue, whatever it might be, when the diamond grinding is done, the floor has a uniform color because the floor has been essentially cleaned of everything that was on top of that concrete slab. The other thing that the grinding does, which is an added benefit, and sometimes it's the objective, is to flatten the concrete. So any elevation inequalities that could cause a problem later, it's going to flatten those out. But basically, it's like sandpaper, but made of diamond for concrete instead of wood. But it's just run on a machine so that it can clean that floor and then also, like I said, smooth it to some extent too.
Can diamond grinding, is it an answer to all situations? Can it grind everything, or does it have limitations?
It definitely has limitations. Diamond grinding is great for doing superficial cleaning. What that means is that diamond is moving laterally across the surface of the concrete. So whatever it cuts across, it can only cut from the top down as it drags across. So if I have a material that is, let's say, 1/4 of an inch thick, it'll eventually work its way through. But there are other methods that would probably be more productive to get through that material. So grinding is not something that can fix every situation, but it's probably the most popular because in most cases, the concrete just needs to be smooth, clean of whatever's on top of it.
So that begs the question, what is a more aggressive method of diamond grinding?
Well, you can do diamond grinding with PCDs. Now, PCDs are a little bit different animal, but it still runs on the same machine. It still runs laterally across the surface of the concrete. But the difference with a PCD is it actually has chips or chunks of carbide that has PCD, polycrystalline diamond, on the face of that holder that drags along and literally gouges the surface. So it's usually going to be more productive than a diamond, which is a small chip. PCD is literally a chunk, so it gouges away at the surface of the concrete.
Is there, what would be the next most aggressive? Say you're dealing with a very thick material that just is too thick or not really advantageous for a diamond or a PCD. What would be the next mechanical process that you would recommend?
Scarification. A scarifier is it's a drum style machine. What that basically means is the tungsten carbide cutters are on a drum like a wood sander, and those tools are driven into the ground. The machine makes a lot of noise because basically it's like a bunch of small hammers that are being driven directly into the concrete from the vertical aspect. So it's actually slamming into the surface of the concrete. It sounds a lot worse than it is, though it is very loud, but it's a very aggressive bulk removal type machine. Not nearly as precise as grinding, but the goal when using a scarifier is because the intention is to remove a large amount, whether it's a superficial coating or the concrete slab surface itself.
Does one mechanical process, is that Is that what you're limited to? Can you combine processes if you get a certain type of a coating that you need to remove, or is it one type of mechanical process fixes all?
It really depends on what's on the floor, what's going to be the most productive method to remove what's on the floor, and what our final objective is for the floor as far as what the system requires for its profile. If as an example, a floor has a thick epoxy on the concrete and grinding alone is taking too long, then it's definitely possible to use the PCD that I spoke of or the scarifier to remove the bulk, because what we're really talking about is a certain thickness of material that's on top of the concrete that grinding alone is not going to be productive enough to remove. So maybe we use the scarifier or the PCD to remove the bulk, 70 to 90% of that material. And then we can follow up with the diamond grinder to remove the rest of the material till it's 100% gone. And ideally leave a smooth surface so that whatever work we have to do with the coating after that, it's not too rough. So certainly you can combine the different processes to do the different types of coatings to find the most productive way to get the floor clean.
One of the things we talked about in our last week's episode was the CSP pads and looking at the different the profiles. I'm not sure if our guests can see this or not, but you can see the difference between a CSP1 and a 9. So the 9 being the much more aggressive. What would you recommend for like something that really was like a CSP 8 or 9, a very aggressive material, or even a 7 through 9? Is there something that's even more aggressive or more efficient than a scarifier?
Yeah, I think it's going to probably be water hydroblasting, actually, which is something that's definitely outside the realm of most applications. That's going to be for like quartz floors, stuff where you're literally taking the top portion of the slab off and replacing it with a whole new wear surface that could hardly be called a coating. Also pressurized tanks, where large amounts of liquid storage, where you need a very good mechanical tooth for a coating because of the pressure that's going to be associated with it. Again, very little to do with a floor, but certainly there are other ways to make a more aggressive profile on a substrate to get a coating to properly bond. But again, that's going to be dictated in the specifications. Most coating systems, 50 mils or less, 1/8 of an inch to 1/4 of an inch, are probably not going to require above a CSP 5.
I was talking with a contractor not too long ago that was convinced that shot blasting was the best overall method for surface preparation. And in some research, you kind of realize there are some restrictions or limitations to shot blasting. Can you go into that a little bit?
Well, with regard to the limitations of shot blasting, a shot blaster it's kind of like a combination of a power washer but dry, or a sandblaster but dustless. So you can imagine when you think of power washing or sandblasting, there's a media accelerated at the surface. Regardless of the size of the machine, that acceleration of media takes place in a small window. So there is some control there of how aggressive it's going to be, but its working ability is based upon the hardness of the material it hits. So if I hit anything that is soft, like adhesive, thicker coating that's made to be impact resistant, anything that will absorb the energy of that media, it's not going to be able to remove it. It may be able to damage it. It may be able to remove a portion of it. But the biggest limitation for a shot blaster would be trying to remove something that's thick and impact resistant, like a thick epoxy in most cases, or thin and elastic, like adhesive. In both those cases, the shot blaster is probably not going to be the best method to remove that material.
Josh, given the limitations of a shot blaster, and in your experience, what do you think the advantages of a shot blaster are?
Well, a shot blaster is going to leave a floor completely clean of any dust, which is really something that a grinder, a bush hammer, a scarifier, a PCD, none of the other tools can leave the floor as clean as a shot blaster, because the way it operates, again, like a power washer, but dry, or a sandblaster, but dustless, is it does its work under negative pressure. So what that means is the waste that it makes while it's working is immediately evacuated from the area where it's been created. So that floor is as clean as it can possibly be. It cannot be made any cleaner by vacuuming it. No matter how many times it's vacuumed, like after grinding, the floor is as clean as it can be. So what that means is that when the coating is applied to the floor, it has the ability to absorb into the surface until the viscosity gets to the point where it can't absorb any further, which is why moisture vapor systems are going to be specified by the manufacturer to have a surface shot blasted. It's the profile is important for systems like that, but what they really like is how clean that surface is. And there's no other equipment that can leave a floor that clean as it does its work.
What would you think is the ideal CSP range for a shot blaster? And what would you expect to see a shot blaster specified?
Normally, they're going to call it a CSP3. But I will say that in the manufacturer literature that specifies the process, if they say CSP3, they're hoping for that, but they know that whatever profile is made, that floor is going to be immaculately clean if the shot blaster is used. Now, some may say a shot blast to a CSP of a 4 or a 5. What's happening with a shot blaster to be able to produce the range of profiles, 3, 4, 5, let's say, is going to be the time that the machine is allowed to do its work over a given space, or how fast it traverses the surface of the concrete, like a sandblaster or a power washer. If you leave the nozzle in one spot, it's going to dig deeper into the substrate that it's being directed at. Shot blasters the same way. So if I blast a room that's 1,000 feet in 1 hour, it stands to reason that if it takes me 2 hours to blast the same space, the profile must be more rough because I've degraded the surface of the concrete to a deeper level. At the top of the concrete sand, and as I go further into the slab, the aggregate gets bigger. So if I need a CSP 5, all I would do is slow that machine down. Now it's going to be very rough, and there probably will be lines in the floor, and I'll have to apply enough material to be able to submerge or bury that profile so it doesn't telegraph through the coating itself. But I can vary the profile that a shot blaster will leave. But anytime that CSP of a 4 or 5 is specified along with shot blasting, I would clarify that with the manufacturer ahead of time.
Okay, I know we're going to dedicate a whole segment for a future episode for shot blasters, but can you just touch on a little bit? I know they make a range of blasters, anything from a small handheld blaster that might be used, for example, stairs, all the way up to shot blasters that are used for road work, asphalt work, and removing tar from airport runways. Can you touch a little bit about what makes them different, what each one, or what's the range of applications they have from small to big, and also touch a little bit about on the various shot that can be used and what's the differences there?
The bigger the machine is, I guess the easiest way to say it is the bigger the machine is, the more power, so therefore the faster it goes. They all work the same way. They accelerate the shot, the media, at the substrate. When it hits, it breaks away a small piece, and then it goes back up through the machine into the vacuum. If I have a small machine, 1.5 horses, or I have a big machine, 30 horsepower, the bigger the machine, the more shot I can throw at the ground. The more shot I can throw at the ground, my production therefore must go up. Of course,
is it the harder it will hit as well?
Harder it will hit is not really the correct way to say it, but from a practical standpoint, yes. The shot is still impacting the ground at exactly the same speed, the same inertia, whether it's with a small machine or a big one. The blast wheel itself is turning at 6,600 RPMs on any of the machines, at least the ones that I'm familiar with. The distance from the ground, because of the amount of horsepower and maybe the volume that's going to be put into the circuit as the motor gets bigger, may be higher. But the whole idea of dismantling that surface of the concrete by shot blasting is precisely done by how fast that shot is accelerated to the ground. And when it hits, the inertia and the mass of the material breaks away that piece of concrete, literally the size of a piece of shot, or maybe a little bit bigger. So the only difference between the small and the big is going to be the amount of power behind it that allows a greater volume of media to hit the ground. It's not like bullets that are flying faster. There's just more bullets. And that's what leads to a higher rate of production. It takes the concrete surface apart faster. Where the science comes into that process is having it still be controllable by the operator, because damaging the surface of the concrete within control is favorable. Damaging the concrete to the point where we have to spend money on material to fix the damage is obviously not favorable. So there is a science behind it, but I guess the easiest way to say it is, whether it's to say it hits harder or there's more power, I just always fall back on the bigger the machine, the faster it will go, because it's the physics of the matter that make the machines go quicker or slower.
And again, the shot itself, does that dictate a bigger profile, smaller profile, more aggressive, less aggressive? Can you make a 30 horsepower machine less aggressive by using a different type of shot?
Yeah, you can definitely leave less of a profile by going with a finer shot, because what's happening with the machines is it's throwing that shot, propelling that shot at the floor. the size of that shot is going to determine the dent or the piece that it takes out of the surface of the concrete. So the bigger that shot is, the bigger the piece that goes with it. Now, again, we're disassembling a slab of concrete that has been made up of sand and rock and whatever. So depending on its current state, whatever condition it's in, a bigger piece of metal, the shot, when it hits, may take a bigger rock or a bigger cluster of sand with it, which then would lead to a more aggressive profile. Perhaps also do it more quickly. There are also contractors that will mix the small shot and the big shot together because they like the idea that a big piece will hit, and then on either side or surrounding the big piece are the smaller pieces. And that complements that bigger one's damage, or as it fractures the surface, the tiny ones around it fracture it even better and leave a little bit smoother profile, despite the bigger piece of metal having done the initial damage. And I'm speaking from the standpoint of almost a snapshot in time. This is happening continuously. This is going through a circuit and it's throwing the shot at the floor nonstop. As it's making the dust, it's recovering the dust in the shot, recycling it, and that process just is ongoing. But certainly you can affect the profile creation with the shot blaster by certain mixtures of shot, but there is no precise measurement that I know of that's been mandated by any manufacturers. It's more of a contractor preference based on what they like to do with the machine, the profile they require, and also the nature of the concrete that they're working with. Because the harder the concrete is, the more that the machine has to be adjusted to be able to handle the disassembly, for lack of a better term, as it creates that profile. Whereas a softer slab, it could be set up for a hard slab and do so much damage to the floor, it's impractical. So the operator really is responsible for how that machine is going to be set up with the shot, the speed, the amount of load on the wheel. It's all in the hands of the operator because the concrete doesn't know any better. It just gets attacked, and then how it comes apart is really going to be dependent on its nature in terms of hardness or softness.
And that actually brings up a very good topic we'll talk about in a later episode as well, is identifying the hardness of the concrete, which will dictate the type of bond of diamonds that you use, or the type of shot, or the speed of a shot blaster. The driving force behind any of the mechanical process is the concrete itself, and we'll talk in a later episode about how to identify that. Well, that's probably a good place for us to wrap up this episode, Josh, and I appreciate it. I'd like to continue the discussion next episode. We'll talk about more specifically about some of the mechanical processes. We'll talk about scarifying, shot blasting, grinding diamond, the different diamonds with diamond grinding, and some of the other mechanical processes as well. But as always, I appreciate your time. I learned a lot, and we look forward to doing this again.
All right, sounds good. Thanks so much for the time. I always appreciate sharing what I've been taught. Thank you.
Thank you.
Thank you for sharing your time with us. If you enjoyed today's educational installment and would like to be notified when we release new segments, click the subscribe button below. If you'd like to suggest a topic for a future episode or have questions pertaining to this week's subject matter, please feel free to leave us a comment. And as always, we invite you to visit us at buymanufacturersdirect.com to view tutorials or purchase some of our industry's most respected and recognizable brands.